Hey guys, my name is Eli Park, and today we'll be doing trigonometry and geometry. First, I'll introduce the three basic trigonometric functions. They are derived by creating a right triangle with angle theta and finding the ratio between side lengths. Let me get my pen. This is blue pen. So, as we can see here, we'll try to first find what sine is. If we have a right triangle with angle theta, sine is the ratio of the opposite leg divided by the hypotenuse. As we can see here, the first letter of each, S, O, and H, makes so. For cosine, we have, for cosine theta, it is the adjacent leg divided by the hypotenuse. So we can see here, C, A, H. And then for tangent, we have tangent theta is equal to the opposite divided by the adjacent. So it is TOA, TOA. So we have the acronym SOHCAHH TOA, and that is how we remember sine, cosine, tangent. So our first example here is asked to prove the statement sine divided by cosine equals tangent. So what we'll do here is we'll try to remember what sine, cosine, and tangent actually are. So let me write down the acronym. SOHCAHH TOA. So let me write it in a mathematical sense. So first I'll rewrite sine. Sine is equal to O over H. And then we also have cosine. Cosine is equal to A over H. So we have O over H all divided by A over H. The H's cancel out, so we get O over A. Opposite over adjacent. And that is exactly what tangent is. So we can say that this is equal to tangent. So sine divided by cosine is equal to tangent, and we're done. The unit circle is a way to remember our basic trigonometric facts and identities. It looks really complex, but let me lead you how to use this unit circle with an example. So our example is evaluate the following expression, sine of 150 degrees. So what we're going to do here is essentially, so this is 0 degrees, and then we're going to take it to 150 degrees. 150 degrees is right there, so we'll take this point, and we'll drop it, and we'll drop that out. So that's the right triangle. So I'm not sure if you can see this very well, but we have this angle of 150 degrees, and now what we want to do is find the sine of 150 degrees of this right triangle. So it is opposite over hypotenuse. So the opposite side is this side. That is actually the y coordinate of this point right here. So it is the opposite of 1/2. And then the unit circle uses the assumption that the radius of this entire circle is 1. So we know that the hypotenuse, which is the radius of the circle, is 1. So we can say that sine 150 is equal to 1/2. Next are the sine and cosine sum formulas. The following are the angles formulas for the sine and cosine of the sum or difference of two angles. This may feel like a lot, but all you really need to know are the first two, and then the later two can be derived from the first two because of our unit circle. I'll show you an example of how. So it says, our example says use the sine addition formula to derive the sine difference formula. Well, what is our sine addition formula? It is this guy. Sine of alpha plus beta is equal to sine alpha times cosine beta plus cosine alpha times sine beta. What we're going to do here is essentially, instead for beta, we're going to plug in negative beta, so we can get something that looks like that, and then hopefully we'll achieve something like that. So I'll write it again right here. Sine alpha plus beta. Oh my gosh, that was a horrible beta. Excuse my handwriting. Sine alpha plus... Oh, that's sorry. Sine alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha. What we're going to do here is for beta, we're going to plug in negative beta. So, hopefully you see how this works. Sine of alpha minus beta is equal to sine alpha cosine of negative beta plus sine of... Actually, I'm running out of room here, so... Oh shoot, I just erased everything. You know what? I'm just gonna... Hopefully you understood what I just wrote, so I'm just gonna rewrite that second line. Sine of alpha minus beta is equal to sine of alpha cosine of negative beta plus sine of negative beta cosine alpha. So essentially what we did here is we took the sine addition formula and then we plugged in negative beta for beta. But we're not done yet here. We have some negative betas within the trig stuff right here and right here. We want to get rid of that. How we're going to do that is we're going to use our unit circle. So let me draw a unit circle right here. A basic sketch. So it asks us, so if we had, like, for example, an angle beta right there, if this makes an angle beta, what is the cosine of negative beta? So negative beta, the angle is going to look something like that right there. And then the cosine of this right triangle is going to be the adjacent over the hypotenuse. The adjacent side is actually the side that both of these triangles share right here. This just side that I just shaded. And then that means that the cosine of a negative angle is equal to the same of the cosine of the positive angle. So actually, we can rewrite this cosine negative beta as just cosine beta. Let's see what sine negative beta becomes. Let me redraw this unit circle. Let me redraw this unit circle for another purpose. So let's say we had an angle right here. And then obviously the sine of this angle is this side over this side. So what we're gonna do is we're gonna take the negative angle again, right here. But now what's different is that the opposite side, which is right here for this guy, is actually negative of this guy. And then since the hypotenuse stay the same, we can say that sine of negative x is equal to, let me erase this. Sine of x is equal to negative sine of negative x. Because what we just saw here is that sine negative x comes over a, and that this is equal to negative of negative o over h. Sorry, this becomes h. So, erasing all this, we can see that sine negative beta is going to become negative sine beta. So essentially we're just going to bring this negative symbol out, this guy out. So we're going to we get to rewrite this as erase. What? They want to erase. What's that? Oh, that's not kind of awkward. Oh, the entire thing erased. Okay, so we get to rewrite this as negative sine beta. That took a lot more steps than if you didn't know. If you had known that the function sine is an odd function, you could have easily just taken the negative out. But I went through the steps of exactly why, without using the fact that it's an odd function. So now, what we have here looks a lot like one of our formulas. Sine of alpha minus beta is equal to sine alpha cosine beta minus sine beta cosine alpha. We see here, this is exactly what we wanted, this guy. So we're done. So next are the double angle formulas. The double angle formula is simply just where alpha and beta are the same thing. So we have, what we can actually just think about this as sine of alpha plus alpha. And this is also similar, cosine of alpha plus alpha. And then, yeah, we just plugged it in, that's how we got it. If you, just for clarity, I'm just going to go over exactly how that happened. So I'll rewrite the sine addition formula. Sine alpha plus beta is equal to sine alpha cosine beta plus sine beta cosine alpha. The way I remembered this is that at the end here, this is sine B. This is a member of a K-pop group called G-Friend. And then right here we have also the Spanish word for thing. Like it just kind of stuck that like these two like connections work, and then like these two arbitrary things that don't really mean anything also stick together. But yeah, that's how I remember it. But what I'm gonna do here is I'm gonna plug in beta is equal to alpha. So for every beta, I'm just gonna replace it with alpha. Sine alpha plus alpha. Oops. Sine alpha plus. Oh my gosh. Sine alpha plus alpha. Sine alpha plus alpha equals sine alpha cosine alpha plus sine alpha cosine alpha. I went a little bit into the blue. Hopefully you see. But you can see here that these two terms are the same terms. So we'll make it 2 sine alpha cosine alpha. And this is equal to sine 2 alpha. This is the double angle formula. So if you have, for example, one angle and you wanted to find the sine of one, if you have one angle, then you can find the sine of double that angle. And similarly, you can, using the other formula, we can find the cosine of the double angle. Our little example here is derive the double angle formula for tangent. This is not as straightforward if you did not know the tangent addition formula, but it's quite simple if you knew it, but I'll just do it without it. So what we're going to do here is, first we're going to, from an earlier example, we remembered that sine over cosine is equal to tangent, right? So, of course, sine of 2 alpha over sine of cosine of 2 alpha, sine of 2 theta divided by cosine of 2 theta must equal tangent of 2 theta. That's exactly what we're going to do here. Tangent of, let me write it here, because it just excessive. Tangent of 2 alpha is equal to sine of 2 alpha over cosine of 2 alpha. Okay, so what we're going to do here is we're just going to plug in the formulas that we have here. So we're going to plug in this for that and that for that. 2 sine alpha cosine alpha over cosine squared alpha minus sine squared alpha. And then the next step here is that I'm, just for simplicity, I'm going to do this. 1 over tangent 2 alpha is equal to the reciprocal of this, which is cosine squared alpha minus sine squared alpha all over 2 sine alpha cosine alpha. And then splitting this into two fractions with this part and this part, I'm going to split into two fractions, and that first one simplifies to cosine alpha over 2 sine alpha minus sine alpha over 2 cosine alpha. As you can see here, we can also use the fact again that tangent is equal to sine over cosine. Right here we have 1 over tangent. Right here we have a tangent. I'm going to rewrite that on the next slide. Wait. Oh shoot. Okay. Ignore this. So I'm going to rewrite this as 1 over tangent 2 alpha is equal to 1 over 2 tangent alpha minus tangent alpha over 2. See, hopefully you see how this is equal to 1 over 2 tangent minus tangent over 2. And then what now I'm gonna put it back. Actually, first I'm gonna multiply each side by 2 to get rid of these guys. So 2 over tangent 2 alpha is equal to 1 over tangent alpha minus tangent alpha. And we want it in terms of tangent 2 alpha, so let's reciprocate it again on the next page. Tangent 2 alpha over 2 is equal to 1 over tangent alpha. Wait, minus tangent alpha. Now multiplying by 2 on each side to get this guy here, and then multiplying a tangent on this top and bottom of the fraction, we get tangent 2 alpha is equal to 2 tangent alpha over 1 minus tangent squared alpha. This is our formula right here, our double tangent formula. This is not greatly useful, but it was a good exercise, using our fact that sine over cosine is equal to tangent, and using our double angle formulas. Okay, next slide. Next is a Pythagorean identity. First, you might not be able to see why this is related to Pythagoras, but the proof will unveil why. Let's use our SOHCAHTOA again. So our statement was sine squared theta plus cosine squared theta is equal to 1. But this is actually sine is equal to opposite over hypotenuse, and cosine is equal to adjacent over hypotenuse. And just expanding the squared out, we're gonna get this. And then multiplying by, wait, let's see if oh shoot, I don't have room. So I'm gonna multiply by h squared on each side. So we're gonna get o squared plus a squared equals h squared. This looks familiar. This is exactly the Pythagorean theorem. In a right triangle with angle theta, this is the opposite side, this is the adjacent side, and this is the hypotenuse. This side plus this side is equal to that side. So we are done. This is our example. It's one of our I edited it so that it's a little more simpler from the original version that I've seen. I've added a radical here, and to make it slightly obvious that you're supposed to square each side of both equations. And hopefully you'll see, you might see why we're doing that. And also we're going to be using our cosine subtraction formula, which is I don't remember it. Cosine alpha cosine beta plus sine alpha sine beta. So working backwards, we can say that we want to find cosine alpha cosine beta plus sine alpha sine beta. This is the quantity that we would like to find. Okay, so let me square the first equation on both sides. Sine squared alpha plus 2 sine alpha sine beta plus sine squared beta is equal to 11 over 8. Doing the same thing on this other equation, we get, oh shoot, it's cosine. My bad. 2 cosine alpha. What? Why is it dotted? What? I'm so bad at math. How do I? Okay, wait, what? I'm so confused. Sorry. Cosine alpha cosine beta plus cosine squared beta is equal to 9 over 8. Let's add them together. This is very promising if we add them together. Because first of all, this looks like the quantity you want to find. And this looks familiar? Well, it's exactly what we just proved. Sine squared theta plus cosine squared theta is equal to 1. So adding them together, we get 1 plus 2 times cosine alpha cosine beta plus sine alpha sine beta. That is exactly what we want to find. So we say that, let's just call x for simplicity, because this is just the answer we want to find. Plus 1 is equal to 20 over 8. Doing some basic arithmetic, 2x is equal to 1/2. So x is equal to 1/4. This is the answer. Wait, did I do that right? Yep, that is right. Okay, so for our next one, we'll be, next one is the extended law of sines. The extended law of sines states for a triangle ABC with lengths A, B, and C, A being opposite of A, angle A, and length B being opposite of B, etc., and circumradius R, which is the radius of the circumcenter, circumcircle. A over sine A is equal to B over sine B, which is equal to C over sine C, which is equal to 2R. So normally the equality of the first 3 terms is called the law of sines, and the equality of those 3 to 2R is called the extended law of sines. First I'll just prove the law of sines. That's my cheat circle for later. So let's say we have a triangle ABC with a height here, let's call it H. This is A obviously, and this is B by definition. So we can say that from this diagram immediately, since let's call this D, you can say that ADC is a right triangle and BDC is also a right triangle. So we can say that sine of angle A is equal to the opposite. Wait, shoot. Don't mix up the H with height. This is just the height over the length B. We can say by multiplying B on the other side, B sine A is equal to H. Similarly, on this side, we get A sine B is equal to H. Guess what? That is equal to that, which means that is equal to that. So that means that we have A sine B is equal to, why did I start writing Greek? Oh my gosh. A sine B is equal to B sine angle A. Obviously we just divide, simple division. A over, oh, I keep writing this out. A over sine A is equal to B over sine B. And then symmetrically, we can just find that using the same proof for the angle C at this stands. Now I'll prove, if I can just prove that this is equal to 2R, it should make sense that that equals that and that equals that. So let's do down the next side. So let's say we had an angle like alpha, okay, and this is the center of the circle. Let me draw a dot. Maybe I make a highlight. What if I did that? That works. And let's draw this diameter from this point here. Notice that this diameter is equal to 2r. So let's prove that sine A is equal to 2r. If you know a bit about cyclic quadrilaterals, you can say that this angle here is equal to the angle here because they have the same arc length. And if you also knew something about about these circles, you can also say that this triangle, since it has a diameter to the side, this is a right angle. So that means that if we have this, so sine of this angle right here, which is equal to sine alpha, is equal to this side over 2r. But this side happens to be A, because it is opposite of angle A. So it's A over this length, 2r. And so, cross dividing, wait, oh my gosh, so weird. Hold on. It's messing up my computer. Okay, I think it works. Never mind. Okay, cross dividing we'll get A over. Oh, I keep doing this stupid louder stuff. Oh my gosh, this is like a very bad habit. I need to fix it. I hope I don't do this in English. I might unconsciously do it. Okay, so that means we have reached this and we have proved extended law of sines. The law of sines is probably one of the most useful of the next few formulas that I'm going to show. Maybe except for like the double angle formula. But let's explore the dangers of it, okay? So we have in triangle ABC, AB is equal to 100, AC is equal to 75, and sine of angle B is equal to 8 over 3. We want to find angle C. So as you can see here, this is AC is equal to the length B. So we can say that, since we're already using law of sines, let's just write this down. 75 over sine of B, which is 8 over 3, is equal to 225 over 8. This is equal to this guy over that. Quite simple. A very direct application. 100. This is equal to 100, which is length C over sine C. Doing some basic math, we can say that I'm very bad at basic math. No, wait. Yeah. And then so we can say that bring this sine C is equal to 32 over 9. These are not the numbers that I expected. That's kind of awkward, because you can't have a sine that's 32 over 9. That's very awkward. Wait a minute. What happened? I think I meant for sine of B to be 3 over 8. That makes sense, right? I think that's what I meant. 3 over... Oh shoot, next slide. I think I meant this to be 3 over... What? I want to use a pen. 3 over 8. Okay, let's try that again. Side B, 75 over 3/8 equal to 25 over 8. This should be equal to C over sine C. 100 over sine C. Oh, these are still not the numbers that I wanted. Oh well, I think this will work though. So just by doing some basic math. Wait, this still doesn't work. Oh, I want to cry. This is very embarrassing. Oh wait, that was actually very embarrassing. This 8 goes up here. So this is actually 1/8. So it's gonna be something like 200 equals 100 sine c. There we go. That's what I intended. So that means that sine c is equal to 1/2. If you're very quirky, you can say that. You'll probably be like, yes, equals 30. We're done, right? Guess what? No, it's not. Unit circle says that yes, that is technically true. If we have 30 degrees here, this is 1/2. This is 3/2. This is 1. So yes, it is indeed. Sine of 30 is 1/2. But that's not the only answer. Since this 1/2 works, where else can it have 1/2? 1/2 could be here. It could be this degree, 150. 1/2. You have to watch out. So c could also equal 150 here. So that's why we can have in this something like this. We had in a triangle we had determined, for example, this length AB, the length AC, this angle B. If we have a side, and angle, we can actually determine what the triangle looks like, because the triangle could look something like that, or something like that. It could be A, B, C could be here, C could be here. You really don't know. Like this, like we had AB is equal to 100, and we had AC is equal to 75. But this is 75, and this is also 75. The angles still stay the same, so that's kind of a danger of the law of sines, and just watch out for that kind of stuff. Our first area formula is a little less trigonometric than what we've been doing, but it's related, and it's pretty useful. What I'm gonna, alright, so this is the P is the perimeter and R is the end radius, which is the radius of the end circle. So this is, oh gosh, let me this right here is R, and I'm going to use that fact to prove this area formula. A, B, C is equal to PR/2. People sometimes write this as SR. S is the semi-perimeter, but it's not as obvious how we prove it if you read like that. So we can see here. Let's call this side A, B, and C. Actually, no. You know, I like this convention. C is here and A is here. So obviously, you can see here the area of this triangle if this is BIC is equal to AR/2. Triangle of AIC is equal to BR/2. Triangle of this guy is CR/2. Factoring out, we get this, and ABC is simply the perimeter, so RP/2, which is the same thing as PR/2, which is exactly what we wanted, so we are done. So area formulas continue. Oh wait, I had the notion of bracket of ABC. So yeah, bracket ABC means the area of ABC. Our next formula is 1/2 AB sine C. So I have a little triangle to help me out. So what we're gonna do is prove that the area of this triangle is equal to AB sine C. So we have as a hypotenuse dropped here, so there's a right angle right there. So the sine of C is equal to H/A, right? Sine of C is equal to H/A. So that means that H is equal to A sine C. Let's go back to the most basic area formula. It's base times height over 2, right? What if we could, so what we do here is that if the area is equal to base times height over 2, or B times H/2, we plug in h here, we get b times a sine c over 2, which is ab sine c over 2. So we are done. Our example here is asks us to find a ratio between triangles ADE, so this guy right here, and ABC. It might not be obvious how we can use the law of sines here to do this problem if you have not done this type of problem before, but watch this. Instead of using the literal formula, let's mix it up a little bit. Instead of memorizing this AB sine C, you're just kind of supposed to know that the product of the two sides and the sine of the angle between them. So like if you have a triangle, A, B, and the angle between it, over 2 is the area. This is how you're supposed to use it. And we're going to use it like here. Let's first try to find this guy. This is going to be 4 times 7 times sine A. Because we don't really have this length here, so it's not very useful for us. So 4 times 7 is 28 sine alpha over 2. And then this is equal to 4 plus 6 is 10, 7 plus 2 is 9, 10 times 9 is 90, so the area of ABC is 90 sine A over 2. What are we doing here? Oh my gosh, the angles canceled out, sine A cancel out, and so did the divided by 2. So, without knowing any of the angles, we used the AB sine C formula, and we found the ratios of these areas. So it is just 28 over 90, simplifies to 14 over 45, and we are done. Our next area formula is going to be ABC over 4R. This is if you remember our last formula, which is 1/2 AB sine C is the area. What we do to this is we use the extended law of sines here, which is C over sine C is equal to 2R. Rearrange this as C over 2R equals sine C, and we literally plug this in here. 1/2 ABC over 2R, which is equal to ABC over 4R. Done. So I think this should be our last area formula, is it? Yeah, this is our last area formula, and this is just Heron's formula. It's not really, it's kind of tedious to prove this formula, but it can be useful because the main thing about this is that you can find the area of a triangle just by knowing the length. You don't have to know anything fancy like the circumradius, you don't need to know the end radius or any angles. It's very straightforward. But the disadvantage is that it could get a little bashy, especially with not as nice numbers. Let's combine the ideas of the last two problems to explore the properties of a special triangle you may have seen in some competitions. The problem is find the circumradius of a 13, 14, 15 triangle. Well, where does the circumradius pop up? In this formula, right? But in order to find the circumradius of a 13, 14, 15 triangle, this is an unknown. We know these, but this is also unknown. So how are we supposed to do that? We just want to find an area, and literally the only thing we have are side lengths. Well, what did I just say? We have Heron's formula. Heron's formula will give us, just by plugging in here, S is the set semi-perimeter, so the semi-perimeter is 13 plus 14 plus 15 over 2 equals 21. 21, the square root of 21 times 21 minus 13 minus 21 minus 14 times 21 minus 15, which is 6. And this is all equal to 84. So going back here, now we know that ABC is 84. Okay? So we do 84 is equal to this times that over 4 times R. a few things cancel out, like that becomes 7, while this becomes 2. This is 12. I'll bring this over and make this a 24. And then now we just switch the positions of r and 24. And so we get r is equal to 13 times 15 over 24. Oh wait, this becomes 5, this becomes 8. So we get r is equal to 65 over 8. I didn't go on to the next page. Nice. Okay, so our last formula here is the law of cosines. You may have noticed that the Pythagorean theorem is a special case of the law of cosines, since cosine of c is equal to 0 if c is equal to 90. So let's explore another triangle that is commonly seen in geometry problems. And it is important that when people make these kind of problems using this triangle, it's kind of hard to do it without knowing this special fact. But I'm just going to show you how, what this special fact is using the law of cosines. So it says that we have a triangle with lengths 5, 7, and 8, and it wants us to find angle A. Well, we can just do here. Instead of memorizing this, we want angle A, but this asks for C. Instead of memorizing this formula, you're just also supposed to know that in this triangle ABC with lengths A, B, C, cosine C, it's this squared plus that squared minus 2 times those two product cosine C, which is the angle between those two, is equal to the opposite squared. So let's make this triangle. This is a rough estimate of what it will look like. 5, 7, 8, which one is it? C, A, B. Yes, right. So we're trying to find this angle. So that is equal to, so that means that this squared equals that squared plus that squared minus 2 times the product of these times cosine A. What's the math? How do you do the math here? Minus 40 is equal to minus 2 times 40 times cosine A, just by bringing these guys over. And we can see that 1/2 is equal to cosine A. That looks very, very nice. The only angle that this works such that, the angle that's less than 180, because A can't be over 180 because it's a triangle. The only angle that this works is 60 degrees. So whenever you see a 5, 7, 8 triangle, just always remember that the angle between 5 and 8 is equal to 60. And sometimes once in the middle of a contest, I've thought about which one is the angle 60, because I forgot and I really didn't feel like doing the calculations again. What I did to remember is that since the angles of a triangle is equal to 180 and 60 is actually exactly 1/3 of it, that means that if there's an angle that's 60 and they're all different, one angle must be bigger and one angle must be smaller. So I drew like a rough estimate and I realized that this is the biggest angle and that this is going to be the smallest angle. So that means that this guy has to be angle 60. Thanks for watching. Find us at Discord on the link to do problems of the days, get math help, or talk about math problems. Our official website is https://cncmath.org. Check it out to get more details about upcoming contests hosted by CNCM. And the music is from this following YouTube link. Very good music. And this was Eli Park, and thanks for watching.